Graphs of polynomial functions are smooth and continuous. Smooth in that they don't have any sharp changes in direction. They're not like V shapes like the absolute value graphs that we looked at before, but they're always curved in nature, along the lines of a parabola, but maybe with more changes in direction. And they're continuous, meaning that there's no gap in between segments. We won't have something like this and then a leap to another part. There are some functions that have those types of jumps, but not polynomial functions. And so what we're going to be doing over the course of this unit is trying to analyze various features of polynomial functions. And so the first thing that we want to be able to do is we want to be able to look at the equation of a polynomial function and to be able to predict whether it's going to take off to positive infinity on a given side or go to negative infinity on the other side, both go in the same direction eventually like we have in the second example, or go in opposite directions like we have in the first. So we want to have a mechanism for predicting that. And for us, we have something that will do that, called the leading coefficient test. Now the leading coefficient test looks like it's going to be a nightmare. We've got this long example of what a polynomial function can look like if we don't really plug in any numbers. The key here is, though, we're not going to look at everything all at once or be distracted by all of this. All we're going to take a look at is the first term of the polynomial function. So what does this a sub n times x to the n mean for us? Well, what it means for us is we're looking at what is the highest exponent of the function. So ignoring everything else, just what's the highest exponent, and then we're going to look at what the leading coefficient is. What is the coefficient in front of that highest exponent piece? So if we had a function like f of x equals x to the third minus 4x squared plus 3x minus 17. What we're saying is we can ignore everything else about this function. All we care about is what is the highest exponent and what is the coefficient, in this case that would be a positive 1, that is in front of that highest exponent piece. And if we know those things, then we can determine which direction the graph will eventually take off to if we go far enough to the right or far enough to the left. It won't tell us what's going on in the middle part of the graph, so we need other analysis to figure that out. But if we want to know whether the graph is going to take off to positive or negative infinity after it's done with all the bumps that are in the middle, that's what this leading coefficient test is all about. So how does it work? Well, let's start off with this first example here. Let me clean up a little bit. So for the first example here, we start off and we say, all right, if the highest exponent, if n, so the n on the exponent for x is even, and that leading coefficient, that a sub n, that coefficient in front of it, is greater than 0, meaning it's a positive. So if n is even and the leading coefficient is positive, then we're going to see a graph along the lines of what we see here. That means that both sides are going to take off and go to positive infinity. Or a statement that you'll be asked to do in your homework is something along these lines, where it says as x approaches negative infinity, so as we move farther and farther to the left, what does f of x approach? Well, as we go farther and farther to the left, our graph is taking off up to positive infinity, so we would say that the output approaches positive infinity. That's what we mean there. As x, the arrow means as x approaches negative infinity, meaning as we move farther and farther to the left, which way does the graph eventually take off to? Well, it's going up to positive infinity. And the same statement can be said for the other side. So as x approaches positive infinity, meaning as we move farther and farther to the right along our graph, as we plug in larger and larger positive numbers for x, which way does our graph take off to? Which way does it go? Well, we can see here it's also going to take off and go up to positive infinity. And the simple reason is, if you plug in a positive or a negative number and raise it to an even exponent, like whatever we're saying n is, if you raise it to an even exponent, then that graph is going to shoot up to positive infinity on both sides, because a negative or a positive raised to an even exponent gives you a positive. If you then multiply it by a positive coefficient, it's going to keep on going positive. So eventually, after it's all done with whatever's happening in the middle, the graph is going to go to positive infinity on both sides. It's going to go in the opposite direction if your highest exponent is still even, but now that leading coefficient is negative. So whereas in this first example here, maybe our highest exponent piece was 2x to the 6th, and then there might be a whole bunch of other things that we disregard and just focus on the 6 being the highest exponent and the positive 2 being the leading coefficient. Now, let's say that leading term was negative 4x to the 4th. So now we still have an even highest exponent. Again, there may be other things coming after it, but we don't care about those. But we have an even highest exponent, but now our leading coefficient is negative. And so if that's the case, then we're going to end up seeing both sides of the graph go down. And so if we take the same statements as we used earlier, as x approaches negative infinity, meaning as we go farther and farther to the left, which way does this graph go? Well, f of x, the output, approaches, it's going down, so negative infinity. And then likewise, as we go farther and farther to the right, so as x gets to be a bigger and bigger positive number, as x approaches positive infinity, then f of x approaches, again, negative infinity. And the reason is, no matter if we plug in positive numbers for x or negative numbers for x into that term, we're always going to end up with negative results. And so if we just plug in large enough numbers, eventually the graph is going to shoot down to negative infinity. Crazy stuff might happen here in the middle. We might cross the x-axis any number of times, but ultimately the graph will go down to negative infinity in both those cases. We're going to refer to these two as touchdown graphs. So as long as the highest exponent is even, then it's going to be a touchdown. It makes sense here, both sides are going up, signal for a touchdown. On the other side here, we can call it an Australian rules football touchdown down under or something like that. The idea here is that both sides, as long as the highest exponent is even, both sides are going to end up going in the same direction. Up if that leading coefficient is positive, down if that leading coefficient is negative. Now what happens if that highest exponent in the polynomial function is odd? So we have n is odd, the highest exponent is odd, and then in this first scenario that leading coefficient is going to be positive. So maybe we have something like 5x to the 3rd power is the highest exponent piece. So again, we don't care about anything other than that highest exponent piece. It's odd with a positive coefficient. Well, in that case, we're going to end up with the following. As x approaches negative infinity, meaning as we move farther and farther to the left, which way is our graph going to go? It's going to go down to negative infinity. F of x is going to approach negative infinity. And the reason for that is if I plug in a negative number here for x, but I raise it to an odd exponent, I'm going to get a negative result. But then when I multiply it by a positive, I'm going to stay negative. So that's why if I go far enough to the left, my graph is eventually going to go down. If I scroll down to give us a little bit more room here, what about the other side? Well, as x approaches positive infinity, meaning as I go farther and farther to the right, my outputs are going to approach positive infinity. So unlike the two up above, now the two sides are going in opposite directions. One side is going down to negative infinity, one side is going to go up to positive infinity. Again, if I plug in a positive number and I cube it, it's still going to be a positive. And then if I multiply it by a positive coefficient, it's still going to be positive. So that's why on the right-hand side here we're going up, whereas on the left-hand side we're going down. Now, if we stay with an odd highest exponent, but now we change that leading coefficient to being less than 0 to being negative, meaning let's say we have something like negative 2x to the 5th, and then again there can be other things in the function, but the highest exponent is 5, but now that leading coefficient is negative. Now what happens? Well, as x approaches negative infinity, meaning as we move farther and farther to the left, which way does the graph go? Well, it's going to end up shooting upwards, so that means f of x is going to approach positive infinity. Now, why is that? Well, if I plug in a negative number for x, and I raise it to an odd exponent, I'm going to stay negative. Negative to the 5th power is going to still be a negative, but then I'm going to multiply it by this negative coefficient. Well, a negative times a negative equals a positive, so that's why eventually the graph is going to end up going up on the left-hand side. Now, what about on the right-hand side? What if I plug in larger and larger positive numbers for x, as x grows to a larger and larger number, as x grows to positive infinity? Well, now I take that positive number and I raise it to the 5th power, and it's still going to be a positive, but then I'm going to multiply it by this negative coefficient, which means I'm going to get a negative result. So that means the output of my function is going to approach negative infinity. My graph is going to shoot downwards. So you can see whenever we have an odd highest exponent, one side is going to go up, the other side is going to go down. It's just a matter of which is determined by whether the leading coefficient is positive or negative. And so we're going to call these types of graphs where one side is up and one side is down, disco. If you imagine, we've got disco dance with the arm up on one side, down to the other. That's what we're going to call this one here. It rings a little truer in person, but this is what we'll go with to describe these two scenarios. Even highest exponent is going to be a touchdown. Both sides are up if the leading coefficient is positive, down if the leading coefficient is negative. If the highest exponent is odd, then it's going to be a disco graph where one side is up and one side is down. It's going to be up on the right and down on the left if the leading coefficient is a positive, and then it's going to be reversed if the leading coefficient is negative.